Well, okay. But in algebra, or in any equation, we're always getting the variable by itself. Yeah, so it's always like x. You're getting x. The problem is, well, first of all, did you guys all track about how I added cosine and combined like terms and then I got cosine alone? Are we good so far? Yeah. Okay. I wasn't done though. That's why there was a dot, 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 because I needed to get x alone. Oh, no big deal. Put a negative 1/2 in your calculator and do divide by costs. No. It's not going to, no. You can try, but no. It's going to put a parenthesis. You're supposed to put something in trig. That doesn't work. But you could think about undoing cosine with an inverse. The problem is, if you go into your calculator and hit cosine inverse of 1/2, you're either going to get a degree or you're going to get a nasty decimal radian. But either way, you're only going to have one answer. But the problem is there's more than one. Now, did anybody actually go in their calculator? Yeah. Okay, what'd you get when you threw it in? 120. Huh? 120. So 120 would be the degrees. Did you guys figure out what that is in radian?
7 pi over 2 pi over 3.
Why do I know it's an over 3? Because it's 60 degrees away. It's a 60 degree. It's 1 pi over 3, 2 pi over 3. Wait a minute. Cheater chart. So, ka, toa. 1, 2, 3, 3, 2, 1. Where is cosine 1/2? At pi over 3's. But wait. That's the first quadrant when cosine is positive. Where is cosine negative? The third and fourth. All student. No, actually. Second and third. C is not included in either one. Now it's weird. We're usually asking ourselves the question, when is it positive? But we're asking this time, when is it negative? Second and third, 2 pi over. Second quadrant and third quadrant, pi over 3 reference angles. That'd be 1 pi over 3, 2 pi over 3, 3 pi over 3. What's this guy?
4 pi over 3.
So if I'm trying to write all possible locations in the unit circle, I'm going to take this, which I should have been able to do from unit circle backwards. And then I'm going to go ahead and say, oh, no big deal. Just make it infinitely many. AKA say all coterminals. Dun, 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 dun. Infinitely many answers right there. This is saying any angle that lands on 120 or, what would that be, 240 at 2 pi over 3 or 4 pi over 3. My guess, some of you guys are working on homework already. If you're checking your odds in the back of the book, my guess is that they're in radians. Are there some in degrees that you found? So my guess is stay in radians, but could you use the degree mode of the calculator to kind of give you some hints or tricks? Yeah, I mean you could. Someone threw it in and got 120 degrees, but if you threw it in and it was in radian, if meaning your calculator was in radian mode, wouldn't you have had nasty decimals? So we don't like getting radians from the calculator. Maybe the degrees would help us, but it might just be easier to do cheater chart backwards and find the right quadrants. Questions on this one? Because it's fairly basic as far as it was a simple add and then get the cosine alone and then undo the cosine. Why is this one? Oh, no, go ahead.
What's n pi?
N is just a quick abbreviation that we've been using since we did coterminal angles. That stood for all positive and negative integers, aka all positive or negative multiples. So it's like 2 pi, 4 pi, 6 pi, 8 pi, negative 2 pi, negative 4 pi, negative 6 pi. So you're getting all those coterminals that are landing on the same exact spot. Is that cool? We can just put n, like technically we should say n for n being all integers, but whenever I see you using this in any way, shape, or form, the n's, I just assume that you mean integers. And remember, once again, some of you guys are trying to go ahead, working on homework, etc. The book is always going to write the shortest, simplest, most condensed versions of the infinitely many angles, which can sometimes be a lot shorter than that. And if they do that, there might be like a pi n instead or a pi over 4n instead, but we'll have to look at that when it comes. First of all, it's kind of warm in here. I'm opening the door, but my question to you is how number 18 is harder. Compare and contrast. How it's the same, how it's different. What was more complicated about it? And some of you haven't even finished it yet, but just looking at it, like, why is it harder? Uh-oh. Our new seat's going to be a fail and I have to change them all up again? Come on. Why is it harder? Good. There's two different sines and cosines. And trig identities, we have some squares in there, right? Now, what did I do? Come on, you took a quiz on this yesterday. What did I do? I plugged in a... Which one is this? What category is that? Where it's a square? Pythagorean. So I plugged in a Pythagorean rearrangement and said that cosine squared is 1 minus sine squared. Where'd you guys go next, or where should you go? Where should you go next? Okay. Come on, guys. You're good algebra students. Don't we at least know to get like all the variable stuff together, right? Okay, so what's next? And if there's nothing there, it's an understood. So what's 1 plus 3 sine squared? Okay, we see the algebra, right? I know there's trig, but do we see the algebra too of once we plug in, the algebra also, once we plug in, we're just trying to get the trig isolated on one side. And Nikki, that was your question a second ago, like what are we doing? Remember, we're trying to get the trig as alone and on one side as possible. And then, well, if we need to in the process, using our identities. But eventually we're going to be using unit circle to get to x. That's what I didn't really make a huge statement of. So that might have thrown a few of you off at the beginning of class. Just a few of you are like, I think I got this one. Okay, go play with that one. But we're not done over here because we still need to divide by 4. Okay. Now we need to actually solve. What do we need to undo first? The squared or the sine? I heard squared 3 times. Is everybody else in agreement? Do you remember that the squared is technically a shortcut notation for this? Why would they write with the squared? Because the sign is stuck until I undo it. This is just a nice shortcut way of writing sine of x, the whole thing, squared. So yeah, technically I do need to square root both sides before I can undo the sign and think unit circle. Which is actually a good thing, because right now sine equaling 3/4, 1, 2, 3, 3, 2, 1, it's not there. But if I were to square root 3/4, now there's a little bit of a struggle. Square root of a squared gives us an absolute value. It's going back to algebra 1, but something maybe not all algebra 1 teachers hit really hard. But what happens over here? How do you square root a fraction again? Yeah, it's like, what's the square root of 9/16? 3/4, because 3/4 times 3/4 is 9/16, right? So use that same idea. You're allowed to take a square root of the top and a square root of the bottom. Do we know root 3? No. Do we know root 4? He's someone I should know. My question is, what quadrants are we looking in if we're saying that absolute value of sine of an angle is positive root 3/2? How do we solve absolute value equations? First and second are part of the answers. Has anybody figured out the angle where this happens? The reference angle? Pi over 3. 1, 2, 3. Yeah, SOHCAHTOA. 1, 2, 3. Here's my root 3/2, and I've got this guy. And so someone said first and second, and they're totally right. And they were thinking that sine needed to stay positive because sine, well, everybody's positive, and then sine is positive. They were thinking he had to stay positive, but why am I going to go ahead and say, oh, guys, you know what? It's everybody. Absolute value. Way back when, if you had an absolute value in any sort of equation to solve, around the variable anyway, to solve, you would have to split it up and make it a positive or a negative. That's where that plus minus comes from. That some of you guys are like, when is he a thing? And when is he not? It's the same. Just fine. Anytime sine is that ratio, positive or negative, we don't care. That squared thing says, hey, I'll take anyone, and I'll make anyone squaring a positive. So who are all those angles? Oh, this is going to be so annoying. How many angles do we have?
4 positive, 4 negative.
We could do 4 positive or 4 negative, but if the directions are just solved, and I'm saying for all, like infinitely many, let's just throw the n on there, and we'll get all of them, and not have to do all the positive, all the negative. Because remember, n can be positive or negative rotations. So we have pi over 3. We have, why not 3 pi over 3?
Because that's
Oh, that's 1 pi. Yeah, that's a whole different location. But 4 pi over 3, that's a thing, right? No, what's the last one?
5 pi over 3.
And what would we have to do to all of these to get the coterminals?
Plus 2 pi 1.
Okay, is anyone already tired of just writing the answer? Okay. This is one of those examples where the back of the book answer is going to be, or at least look a lot different than yours, because it's not going to have 2 pi n's. Because they say, yeah, no, we're not going to write 4 different expressions for one answer if we can help it. And here's how they can help it. If you were to look in the back of the book and see a plus pi n, instead of a 2 pi n, a pi n, how much of a circle are you going around if you're just adding pi? Half a circle. So 2 pi n said, hey, start here, n back there, n back there, n back there. But wait, if this is also an answer, what would happen if we added pi to pi over 3? Wouldn't we get 4 pi over 3? Do you see it? I can take the first quadrant one and the third quadrant one and say, how far apart are you guys from each other? Pi, 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 pi. I can add 1 pi's, 2 pi's, 3 pi's, 4 pi's, 5 pi's, 6 pi's, and I can get both locations. So if I just say, hey, I'm only going around half as much, 1 pi over n, 1 pi plus, remember n is all positive or negative integers, so pi over 3 plus 1 pi plus 2 pi plus 3 pi plus 4 pi plus 5 pi. I'm not talking about full rotations anymore. I'm talking about half rotations, and I'm able to check off both of those, because if I'm going halfway, I'll get the first quadrant and the third quadrant. So what else do you think they're going to have as their answer? Who's left? 2. Yeah. They could do the exact same thing with this guy. Now, there are a couple different reasons why they might actually decide to even be snazzier. Do you guys see how 2 pi over 3, this guy, would go ahead and connect to that guy, right? Pi, 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 pi. But here's the crazy thing. They say, you know what? I could be even shorter in how I write this if I go up pi over 3 plus pi n and down pi over 3 plus pi n. Technically, it means the exact same thing as this, but they say, I can make it even shorter. Just check it. Wouldn't this give us the first and then the third? And then wouldn't the negative give us the fourth and then the second? It's kind of annoying how efficient they try to be sometimes. But they're just taking a very valid answer. They're just taking a very valid answer and saying, I can write it shorter, and then being like, I can write it even shorter. So were you wrong to begin with? No. You could write this.
Okay.
Yeah, you can write that. That's totally fine. But when you go to check the answer in the back of the book, will you be able to look at theirs and be like, ugh, they're just trying to be efficient? Does that make sense?
So is the 2 pi n going to be in all our answers?
In all of your answers? Possibly. In all of the book's answers? Not necessarily, because if they could write it shorter, they will.
I don't understand what the 2 pi n is for.
Oh, because if you're trying to find all places where, what was that, sine? Oh, all places where sine squared is 3/4. You could spin 20 million times and land on pi over 3, and the sine will be square root of 3 over 2. So if they're asking for all possible ways or all possible places or times or rotations that land, you're like, there's infinitely many. So instead of like starting to list off 60 and then 120 and then 240 and then 300 and then having to say 360 plus 60 420 instead of having to list off all of them and just keep on adding we put in a little baby formula to say okay so this is the main location and you can spin however many times you want and land there and it's going to still be correct. Does that kind of make sense? Yeah. So it's taking the infinitely many coterminal angles and saying you know what all of those one location. I mean sometimes it'd be nice to just graph it and say I don't know any angle that lands there. This is the mathematical way of saying it. Kind of. And why is it 2 pi? To get you all the way around. Why are they saying I can shorten it in pi? Like, well, if you go halfway, you'll get the other answer too. And halfway. Now, hold on. But the example right before, the problem right before, this one, why didn't I show you that whole crazy plus pi n thing? Could they shorten this anymore? Not really, because if you added pi to the second quadrant, where are you going to end up? If you go half a rotation from the second quadrant, where are you going to end up? Fourth quadrant. And are there any answers in the fourth quadrant where cosine is a negative? No. So they couldn't have done that plus pi n trick and like condensed it. Now, they could have, well, sinkers, they could have still done that trick of, well, you could go up 2 pi over 3 or down 2 pi over 3. They could have done this if they wanted to. There's technically giving us 2 answers in one. So they could have done it this way. But they couldn't have gone only half a rotation because in the unit circle, or just thinking about angles in general, half a rotation from this guy, the cosine is no longer a negative. Cosine is positive in the fourth quadrant. So the only way they could have shortened this is like, oh, guess what? 4 pi over 3 is the same thing as negative 2 pi over 3, and I can make it shorter. They just like trying to rewrite it to make it shorter. So if you get to a problem in the book where you're checking an odd, because if you're checking an even, I'm here, you can ask me. But if you're checking an odd in the back of the book or on Calc Chat, just realize you might have your answers written one way, with like plus 2 pi n. They might have it written another way. All you need to do is go to the unit circle and just ask yourself, is it talking about the same thing? 2 pi over 3, negative 2 pi over 3. It's the same locations as these two guys. Or like the ones that Nathan just said, like he's like, can I just write the long version? He totally can. Just make sure in the unit circle that when you're talking about first, second, third, and fourth, and they say first, and half a, third, and second, or negative, fourth, and half a second. Just make sure that they're landing in the same places, and then you're good to go whichever way you wrote it. I feel like some of you are super confused, but it's just because they have nicer, neater, simpler ways of writing some of the answers. Okay? Ish? How did the directions just change?
So,
Yeah, this is solved for all. This is solved for all within a certain limited domain. Yeah? So it's like last night. I was headed home after working out, and I was hungry, so I went to the Wendy's drive-thru, right? And are there a lot of options on the, I don't usually go to Wendy's actually, but it was the only thing on the way home that was still open. Are there a lot of different options on the, what's it called? The menu, ordering, thingamabob, billboard, that thing, right? The menu. Are there a lot of options? Yes. My brain went to the little value menu. There are a lot of options, but I was only looking here. Does that make sense? So, there are a lot of options. This one says, give me all. And it's like, for math, there are infinitely many because you can spin however many times you want. So I use these little formulas to shorten it. But this one says, no, only look here. Your parents sometimes do that. Like, you only have this much money to spend, so whatever, right? Or like allowances or whatnot. So what if I was to say negative pi to 2 pi? Before you ever stress about the problem, can you just think about what angles I'm asking for? If I tell you on like a fast food menu, like, okay, go to the value part, well, that's good for anything but like In-N-Out. They don't really have a value part. Chick-fil-A doesn't really either. But anyway, most of them have like a little value menu, right? If I'm telling you in your answers to only look here, you have to know where to look or else you're going to get them wrong. So Here's my advice. Whenever they give you some sort of only look here restriction, think about it starting at 0. Starting at 0, how positive am I allowed to go? 2 pi. Isn't that one full rotation? Okay, so I'm allowed to look in the first, second, third, or fourth quadrants in a positive way. But where else am I allowed to look from 0? Okay, so if there are any answers in the third or fourth quadrants, I'm going to have to give it in a positive angles and give it in negative angles. Those are the angles I'm looking for. Now, I have to come back to the math and say, oh, stink, I'm supposed to figure out what's going on. And so looking at the math, technically, why have I split up and set 2 different expressions equal to 0? I'm going to make it a little bit nicer. But why am I setting 2 different things equal to 0? This has nothing to do with trig and everything to do with algebra. Why am I doing this? What's the only way that can be true? Either he's 0 or he's 0, or they're both, one of them has to be 0. Anytime you're multiplying in math, one of them has to be 0. So if we have something like x plus 1 and x minus 3, oh, that's why we would take each of these and solve for their zeros. One of them had to be 0. What's going on in between these two right now? Multiplication. And if it's multiplication, what am I supposed to be doing then? I'm going to be dividing in just a second, maybe to some of them. But multiplication, I'm going to be splitting and setting each one equal to 0. So I'm taking the factors, which is kind of like dividing, taking the factors and I'm setting each one equal to 0. One of them has to. Now this one's pretty easy in the sense of getting the trig alone. And ironically, this one's easy in getting trig alone. You just don't like it because there's a 2 there, but it is what it is. The trig is alone. The 2 is stuck inside right now. You can't go tackling that bad boy. Until you get rid of, well, we got to get rid of, in both of these, the cosine. How do we get rid of the cosine in both of these? Inverse cosine. So think about it backwards. Come on, cheater chart people. Are you making the connection? How'd you get there so fast? Sine, cosine, 3, 2, 1. 1 is that pi over 3. And we've already talked about it earlier too. Wait, we literally just did this one. Hold on. Whoa, whoa, whoa. We just figured out that this is going to happen in the, you guys said the second and third quadrants, right? At pi over 3s? The nice thing is I made it so this guy showed up again because you already solved him a second ago. So we know this one is going to get me pi over 3. I'm not doing plus 2 pi n, because if I went a full rotation, I'm too big. I'm outside the boundary, so no, it's illegal. I can't do it. Oh, but why don't you go, wait, okay, so why don't you go this guy? Can't you go negative? Oh, wait a minute, pi over 3, cosine's not a negative at pi over 3, is he? Isn't that first quadrant? Who is this guy in the second quadrant? 2 pi over 3, and, oh, struggle, wrong one. And who's the one in the fourth quadrant? Yeah, so I wrote the wrong ones down. So 2 pi over 3 and 4 pi over 3. But why am I also going to write negative 2 pi over 3, but then I'm going to stop? Yeah. I'm stuck, I'm bounded by that pi, that negative pi, and then I'm done. So I went positive 2 pi over 3, positive 4 pi over 3, negative 2 pi over 3. I can't keep going because it would be beyond my boundary, so okay. I have those 3 answers. And that's it, but I still haven't undone cosine over here yet, right? If you guys want to put a label on this, it might not be bad to do in a highlighter. This is actually an example of solving a multiple angle equation. As soon as you see this 2x, it's not just an x, it's a 2x. Just looks funny. It's called a multiple angle equation because there's some sort of multiple inside the angle part of this whole thing. Might be a bonus on the test sometime soon. But I undid the cosine on that side. Now I have to do the work of thinking unit circle on this side. So I'm going to do green just to keep it different from the blue. When is cosine 0? 3, 2, 1, 0. Where's that at? Cheater chart people. It's not that bad, you know. You can also think when is x 0? X is 0 at 90 and negative 90 at pi over 2 and negative pi over 2. Okay, so if I know that that's at pi over 2, hey, sweet. Pi over 2 is totally within my 0 to 2 pi restriction. Hey, wait a minute. Isn't 3 pi over 2 also a 0 of cosine? Oh, okay, so I have pi over 2. I have 3 pi over 2. And I also have negative pi over 2. Okay, I'm done. Is x alone yet? Okay, fine. X isn't alone. How do we get x alone? Yeah. And here's the kind of crazy thing that some of you are going to start to get really mad at. If there's a multiplication by 2 on the inside, isn't that a horizontal shrink by 1/2? Doesn't that mean that what used to be 1 full cosine between 0 and 2 pi is now 2 full cosines? And this, or for this, it might be really helpful to show a slide that I kind of just pushed off, I don't know, towards the end somewhere in section 5.3, where I had, oh, I don't even know where I put him. Here he is. Where I was trying to show about visualizing solutions. If you're ever technically trying to solve one of these things where it's like cosine equals negative 1/2 or cosine of 2x equals 0, technically what you're doing is you're giving it a certain y value like negative 1/2, which would be down here, or a certain y value like 0, and you're saying, okay, for how many places, how many times, how many angles would this intersect the curve and where? Now this is with sines. That doesn't really help you tons and tons and tons. We've been thinking mostly unit circle and where these things are true, but you could also be thinking about the waveform of these trig and for what horizontal lines, for what intersections these values would have. I'm going to kind of use that idea in solving this one because if I was to show you pretty quickly, let's see if I can get this extra page in. Wrong direction. If I was to get a cosine curve in, not that you guys are necessarily like complete champs at cosine curves, but if I was to get a cosine curve in here, but a cosine 2x curve, that means I would have a cosine going up 1, down 1, being totally normal, except he's been squished in to have 2 cycles where he would normally just have 1. And I'm actually allowed to go back to negative pi also because of my restrictions. Here's the struggle. How many times will cosine equal 0 now that it's been squished? 1, 2, 3, 4, 5, 6. I only have 3. There are twice as many because of the multiple angle. There are twice as many answers. And here's one way you could see that. We could have just written this as pi over 2 plus 2 pi n and 3 pi over 2, those two different locations, plus 2 pi n. And then we could have said 2x equals and 2x equals. If we divided everybody by 2, we're going to start getting pi over 4s and 3 pi over 4s. The crazy thing is everything just got cut in half, including how long it takes. So it's going to be repeating every pi instead of every 2 pi. Now this might seem really like ethereal, abstract, out there, what do I actually do with it? But the nice thing is it's not really all that crazy. It just means you go twice as far as you normally would in getting your answers. So I'm going to say 2x is equal to pi over 2 and 3 pi over 2. Great, but you're not done. Keep going to 5 pi over 2 and 7 pi over 2 because when I divide everything by 2, they technically all fit now. And I'm going to go ahead and go that negative direction also. Negative pi over 2 and negative 3 pi over 2. I'm going to go twice as far as I normally would. Because when I divide by 2, they're going to fit. And my final answers are going to be, which is kind of crazy because there are a lot of them, but we saw they're supposed to be what? Like 6? X equals pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Now guys, I've technically shown you like exceptions. Some weird examples with like squares and absolute values and plus or minuses and like this multiple angle thing where there are twice as many answers and we have to keep looking. Some are much more fundamental, some are much more basic in a sense. I realize other teachers let their students out early. I'm sorry they're distracting you. But just trying to make sure you guys are all like in line for what we're doing tonight. There are a lot of examples that we haven't done. I don't know if you need them per se, but I don't want you to necessarily feel the pressure of having to turn in homework to Google Classroom without them. So, tonight you need to start this homework. It's going to be really painful if you don't. However, I'm going to take the pressure off of it being due at 8 a.m. tomorrow finished. Okay? So, Google Classroom will be due on Thursday. Yeah, I'll change that. No, tomorrow is Thursday. Due Friday at 8 a.m. as far as completely attended. But we're going to come on in tomorrow, and you guys hopefully will have gotten stuck on some and been like, so that when we do examples, you can be like, hey, it's like mine, can we look at the homework one, and I can answer those questions. Sound good? Here's the crazy thing. Did I really teach anything new today? Not really, but I reminded you how important unit circle is, that we're going backwards from it, and the one new thing was this multiple angle craziness that we will probably deal with more tomorrow. Bye, guys. Way to hang in there. Unit circle, please. It's back. Review it. 1, 2, 3, 3, 2, 1. Do you know what that means?